All right, 2.4 is structure of metals and alloys. We're going to be talking about some factors that impact metallic bonds, and then we're going to talk about something called an alloy, which is a mixture of metals. We talk about metals in terms of the sea of electrons model, or the electron sea model, depending on who you ask what they would call that. In metallic bonds, the valence electrons of the interacting metals atoms are delocalized and they are mobile. They're free to move around. So when we say delocalized, that means they're no longer singled out around a certain atom. They're shared amongst a lot of nuclei. They're delocalized. When we say that they're mobile, that just means they move rapidly and freely from one atom to another. That is to say, instead of orbiting their respective metal cations, this is what delocalized means. Instead of orbiting their respective metal cations, instead of just orbiting one, they form a sea of electrons that surrounds the positively charged interacting metal ions, so they can flow all the way throughout the network of metal atoms, metal cations. The electrons then move freely throughout the space between the metallic cations. The valence electrons in metallic solid are delocalized. They provide a strong cohesive force that holds the atoms together. So those electrons that are freely flowing throughout the network do hold a strong attraction to the nuclei, and that holds it together in a strong cohesive force. Some other properties of metals: due to the movement of the electrons, substances that exhibit metallic bonding have shiny luster. This is because those mobile electrons have a higher reflectivity than electrons around a single atom. Due to the motion of the electrons, metals are capable of conducting heat as well. This is because heat is moved and transferred through the moving electrons. Because those electrons are moving, they can conduct the heat from one side of the metal to another. Electrical conductivity can be explained by the ability to conduct electricity too. Metals conduct electricity due to their free-flowing electrons and the charges that were created when the electrons became delocalized. Here are some more properties of metals. Malleability. That's the ability to bend without breaking. Ductility. That's the ability to be stretched into thin wires. Since metallic bonding is not rigid like ionic bonds, and the electrons are mobile, they're not bound into a structure as it is in an ionic bond, metal atoms can slide over one another to form new shapes, and they can bend and move past each other much more easily than in, say, an ionic bond. So you remember the picture that we had of the ionic bond, that those like charges would cause them to repel. Remember, this blue area in here is our representation of free-flowing electrons between these positive nuclei. And because of that, that repulsive force doesn't have as strong of an effect. And so if we were to hit a row of these atoms with a hammer or some other sharp external force, the metal will be deformed. It will just kind of move in a different shape, and that sea of electrons will still just flow around the nuclei. The melting point of a metal is most closely related with the strength of the metallic bonding present. So how strong is your metallic bond? That is how we're going to tell whether we're going to have a higher or a lower melting point. The more delocalized valence electrons exist, the stronger the metallic bond is going to be. So if we have more delocalized valence electrons, we'll have a stronger metallic bond. And the stronger the metallic bond is, the higher the melting point is. So here's an example. I have Na and I have Mg. Mg has twice the number of delocalized valence electrons as Na because it's got 2 valence electrons and Na only has 1 valence electron. Therefore, magnesium has a stronger metallic bond than sodium because magnesium has a greater sea of electrons. And the melting point of magnesium should be higher than the melting point of sodium. Now let's talk about alloys. An alloy is a mixture of metals or a mixture of a metal and another element. So a pure metal, if you look down here at the bottom right, a pure metal is just all the same atom, same metal. Then we've got these words substitutional alloy, interstitial alloy, and a substitutional and interstitial alloy. We're going to define the difference between those three, but a mixture of a metal and another metal or a metal and another element is going to be called an alloy. The relative size of each element in the mix plays a primary role in determining which mechanism will occur. When I say mechanism, I mean what type of alloy is it? Is it substitutional or interstitial? Let's define those terms. And we're going to be comparing, when it says the size is what we need to pay attention to, the relative size, we want to compare the atomic radii of the different elements in the mixture. The first type of alloy is called the substitutional alloy. That sounds, it kind of sounds like what it is. Substitutional, it just means there's a substitution that is taking place. That's when the atoms are relatively similar in size. So you see this top right example. The atoms are not very different in size. They're a little different, but they're pretty close to the same size. The atom exchange method usually happens where some of the atoms composing the metallic crystals are substituted or switched out, so they're substituted with the atoms of the other constituent. This is called a substitutional alloy. Then we have the interstitial alloy. That's when one atom is much smaller than the other, and it can't successfully substitute for the other type of atom in the crystal of the base metal. The smaller atoms become trapped in the spaces between the atoms of the crystal matrix called interstices. This is called an interstitial alloy. So this example on the bottom left is an interstitial alloy. We've got a much smaller element that is being mixed in with another element with much larger atoms. The best place for those to fit, for those atoms to fit, is between the other atoms in those gaps or spaces we call interstices. Substitutional and interstitial alloy is when we have a little bit of both. That's a combination of both substitutional and interstitial alloys. So if you've got more than 2 elements, it's possible that you would have a combination where some of the metals are just being substituted, substitutional, and some of them are fitting in those little spaces between, and we call that an interstitial alloy. So the next table, you can try it on your own and check your answers. Because these are the same size, we would say this is a substitutional alloy. Iron and carbon, there's a pretty big difference between their size. This is over double the size, so we would call that an interstitial alloy. Fe and carbon and nickel and chromium. Well, Fe and carbon, iron and carbon, that's interstitial. But then the others are pretty close to the same size as iron, so we would call those substitutional. This is substitutional and interstitial. And then finally, 145 and 142, very close to the same atomic radius or ionic radius, so it's a substitutional alloy. All right, the properties of alloys versus properties of metals. There are some similar properties. They both are lustrous and good conductors of electricity and heat. Some different properties are things like malleability and ductility. In an alloy, the addition or the substitution of the other metal atoms causes the atoms to have more difficulty sliding past one another, especially if you look at an interstitial alloy like this. It would be harder to get this plane to slide past with those atoms wedged in between than it would be if it was a pure metal. So it makes it a little bit stronger and not as malleable. Alloys, especially interstitial, are harder and more rigid, while pure metals are more malleable, ductile, and soft. That's it for the metal notes. You should be able to finish the rest of the practice that you received on Thursday or Friday of last week.